In this video, we will be talking about hydrocarbons. This will work on our learning objective for learning how to draw expanded, condensed, and line angle formulas for our hydrocarbons, and identifying the molecular geometry around each, as well as classifying our carbons as primary, secondary, tertiary, or quaternary. So what are hydrocarbons? Hydrocarbons are organic molecules that are composed completely out of hydrogen and carbon. And that's exactly how it got its name. Hydrocarbon literally just means hydrogen carbon. Saturated hydrocarbons contain the maximum amount of hydrogens possible. So it's like they're saturated with hydrogen. Saturated hydrocarbons are also known as alkanes. So we'll be talking about alkanes quite a bit. You can see in the figure for octane over here, octane is an alkane. It ends with ane as well. And the chemical formula for octane is going to depend on the number of carbons. We know that carbon will bond to enough things that it has 4 total bonds. And so the number of hydrogens in a saturated molecule like this will be twice the number of carbon atoms, and then we'll have an additional 2 off to the side. So that's going to follow our 2n plus 2 rule. So the chemical formula for octane will include 8 hydrogens, and 2 times 8 is 16, and so 2 plus that is 18. So if we counted up all the hydrogens here, there would be 18 hydrogens. That's true for all acyclic alkanes, meaning not ring-shaped. So acyclic means not cyclic. Cyclic would be if they formed like a closed ring shape, like a pentagon or a hexagon shape. And so that rule only applies to acyclic things, not cyclic. Because on the cyclic ones, the ends are connected. Not all hydrocarbons are saturated. Alkenes are what we call unsaturated hydrocarbons that contain a double bond somewhere in the structure. And alkynes, that's pronounced alkynes, contain a triple bond somewhere in the molecule. So unsaturated hydrocarbons means that it does not contain the maximum number of hydrogens. Aromatic compounds are also unsaturated. Aromatic structures have alternating double bonds in a 6-membered ring. So this one is saturated. This carbon is saturated because it has 4 single bonds. This is unsaturated, and it's an alkene because it has a double bond. This is also an alkene because it also has double bonds. This is an alkyne because it has a triple bond. Hydrocarbons can come in all shapes and sizes. You can have straight chain alkanes, and you can have branched alkanes. We call them branched because it's like a tree with branches coming off. You can also have cyclic structures where it forms a closed shape. You can also have double bonds in a cyclic structure, and then you can have an aromatic structure where every bond it's alternating double and single bond in a ring. And aromatics have a special properties, and so they're their own class of hydrocarbon. In the earlier slide, I showed you that you can have branched alkanes. We can classify the carbons to indicate the degree of branching. So a primary hydrocarbon here is only bonded to one other carbon. If it's bonded to only one other carbon, then this would have 3 hydrogens on it, or whatever. The point is that it only has one other carbon bond to it, and that's primary. A secondary carbon would have 2 other carbons bonded to it, and then 2 bonds to hydrogen or something else. This has 3 other carbons bonded to it, and so that's tertiary. And this one has 4 other carbons bonded to it, so this black carbon in the center is a quaternary carbon. Now we can have those degrees of branching, and when we are trying to express our branches in condensed structural formulas, we can either draw the branch up or down to indicate where the branch is located, or we can use parentheses to indicate that that's bonded to the previous carbon. So you can see it says CH3, CH, and then parentheses CH3. That implies that that CH3 is bonded to the previous carbon, because we're reading off the carbons like a book from left to right. Practice converting this line angle structure into a condensed structural drawing. Unpause the video when you're ready to check your work. Okay, so I see this coming off, and then I'm going to treat that as a branch and that as a branch. So I see 1 carbon, CH3, second carbon, C has 1, 2, 3 bonds, so it must have only 1 hydrogen. It has a CH3 branched off of it. Then continuing down to here, that carbon has 1, 2, 3 bonds already, so it must only need 1 hydrogen to get up to 4 bonds. Then it has this branch coming off of it, and so that has, open parentheses, this carbon here has 2 bonds already, and so it must have 2 hydrogens to get up to 4. So that's a CH2. And this one has 1 bond, and so that's going to need 3 hydrogens to get up to 4. I should not have closed the parentheses yet. There we go. All right, now I can come over here, and this one is also going to need 2 hydrogens, so it's a CH2, and this is going to need 3 hydrogens, and so that's going to be a CH3. So what are isomers? Isomers are molecules of different chemical compounds that have the same molecular formula. What makes them different compounds is that the order or arrangement of the bonding is different. There's a flow chart to classify all of our different types of isomers. For now, we'll be focusing on the constitutional isomers side of the tree, which are also known as structural isomers. Here are examples of structural isomers that all have the chemical formula C10H22. The more carbons you have in a molecule, the more possibilities you have for the number of isomers. So the structural drawings need to convey how the atoms are connected together. And so the order matters. When you're trying to write out your condensed structural formula, you do need to convey what's bonded to what. You can't like merge all the CH3s together when they're not bonded together. And then it says, can you draw another isomer of this compound? So let's try to think. Let's try to first see what we have here. This has 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. So there's different possibilities here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think that one's different than anything that's down here. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Long. Yeah. That one's a bit different than anything that's down here. But there's lots of them. But we also have to be wary that not all of our structural drawings do represent different isomers. There's also different conformations of the same molecule. Imagine a piece of spaghetti. I could pick up this piece of spaghetti and drop it, and then it might end up in a different orientation. And so that same noodle, it can land in a whole bunch of different ways. So we need to be aware of the fact that single bonds can rotate within our molecule, but double bonds and triple bonds cannot rotate. Since single bonds can rotate, we can take this same molecule and rotate it around so that it looks different. We will learn how to count when we get into the nomenclature, but counting is essential to identify which carbons things are on so that you can learn to recognize that this branch always occurs off of the third carbon from one end. Once you recognize that this branch always comes off of the third carbon from one end, it's easier to see how all of these are the same molecule. It's just how this part of the spaghetti noodle has bent around that makes it look different. But we need to learn to recognize our molecules, whether they're facing up, whether they're facing sideways, whether they're facing down or the other direction or diagonal. So we gotta recognize our molecules from all different directions because they could be drawn from any direction. So now we get to play a game called Isomers or Not. Do the structural formulas below represent the same compound or different isomers? Go ahead and pause the video and try to think for yourself whether these are isomers or not. Unpause the video when you're ready to check your work. Okay, let's go over this. This molecule is 1, 2, 3, 4, 5, 6 long. This molecule is 1, 2, 3, 4, 5, 6 long. And single bonds can rotate. So this is drawn down, but it could have been drawn across just as easily. So these are the same molecule. Down here, if we try to find the longest chain of carbons, this is 1, 2, 3, 4, and I'll call that one number 5. And so I have this hanging off of the fourth carbon, and I have this hanging off of the second carbon. Let's try to name this one, or number this one. 1, 2, 3, 4, 5. So it's 5 long like the previous one. And this is hanging off of the fourth one. This one is hanging off of the third one. So 3 and 4 are right next to each other, and 2 and 4 are not right next to each other. So this carbon here is separating the branches, but in this molecule there is no carbon separator. And so these are different bonding arrangements. These ones are isomers. And so we'll call them constitutional isomers.